Okay, YouTube, in this video we're going to be looking at a general method that we can use to solve larger systems, most specifically systems that have three equations and three variables. And so in this instance we're going to refer to these as 3 by 3 systems. You'll often see it written as 3 by 3. But what we're going to be looking at, just like when we solve 2 by 2 systems, is we're going to be looking for an x and y and a z combination that if I were to plug it back into any of these equations right here, it would satisfy all of them, or we would get true statements for all of them. So first things first, our solution is going to be referred to as an ordered triple. And this ordered triple, just like an xy point, is just a little bit longer. It has an x, a y, and a z. So our goal is going to be to look for this solution to the entire system, but do so algebraically with this 3 by 3 system. So algebraically, we're going to start with just what our goal is algebraically in order to find our solutions, and then interpreting that solution. So we say our goal will be to systematically eliminate the same variable, but using two different sets of two equations. Now, when you look at your original system, one thing I want to have you do is this. Off on the left of your first, second, and third equation, let's put a 1, 2, and a 3 with a colon here and underline it, just to indicate that we have three equations. And in an effort to keep our work very organized, what we're going to do is this. Whenever we rewrite any of our equations, we'll put a 1 or 2 or 3 next to it to indicate which of the three equations it came from to begin with. So when I say that we're going to systematically eliminate the same variable using two different sets of two equations, I kind of mean that we're going to pick two of these three equations at a time and use just those two equations to eliminate, say, the x's or the y's or the z's, but just two equations at a time. And we're going to do this two different times with two different sets of two equations. So let's start with this. First things first, when we solve a system of three equations and three variables, perhaps we put kind of like our steps over here. And so to make this a little bit cleaner, let me do this for ourselves here. I'm going to put in a text box. I'm going to say 1. We are going to select the variable that we would like to eliminate. So in this case, when I look at my system over here on the left, I'm looking and I'm seeing like what would it be easy to eliminate, our x's, y's, or z's. And so because all of my x's have 3's in front of them already, I think it would be easiest to manipulate those so that they cancel out. So I'm going to choose to eliminate x, and in this case, since I have to choose just two of my three equations, I'm just going to go with equations 1 and 2. So because I've selected the variable that we'd like to eliminate here, the next step was, or is, to select two of the three equations, rewrite them off to the side, then eliminate the chosen variable. So essentially, when we look at this as a process, we're going to start by saying, I want to cancel this out, and now that I know what I want to cancel out, let's choose two of our equations. So the way this would look is this. I'm going to say I'm going to use equations 1 and 2 because it doesn't really matter. They both have a 3x on them. So I'm going to say 3x minus y plus z equals -1, and then I have 3x plus 2y minus 5z equals -16. Now, one thing I want to say about this is you should always rewrite them first, like we've done here, and then we're going to go through and manipulate them. So what I'm going to do is, it says, then eliminate the chosen variable. I wanted to eliminate my x's. So because I already have 3's on both of these, I need one of them to be negative. How about we take the top equation times a -1? And so what results is this. We're going to rewrite our system, and we get -3x in the first equation, positive y, negative z, and a positive 1. And our second equation becomes 3x plus 2y minus 5z's equals -16. So this whole eliminate the chosen variable thing, once I've done this here, we get some new equation that is, in this case, 3y minus 6z equals -15. And what I want you to do is I want you to put a box around that. I'm going to make my box a little cleaner here. So we say put a box around this, and don't lose it because we're going to need this equation later. But the profound thing about this is we eliminated one of our variables, leaving behind just y's and z's. Now, for our next step, once we've eliminated that there, let me put in our text box over here. So for the third step, what we're going to do is this time. Choose, maybe I can change my colors here. I can't, and so just give me just a moment here. I'm going to change back over to text. You know what? That's okay. We're going to choose two different equations than the ones that were chosen in step 2. And so essentially what we're going to do is this time we're still going to eliminate our x's. But this time, instead of using equations 1 and 2 like we did last time, we're either going to use equations 1 and 3 or 2 and 3. So maybe in this case, again, they're all 3's. It doesn't really matter what I pick. Maybe in this case what I'll do is I'll use 1 and 3 as my 2 equations. So again, just like I did last time, I'm going to go write these over here, and I'm going to make sure I label which ones they were. So equation 1 was this 3x minus y plus z equals -1. And also the third equation, which is 3x plus 3y plus 2z's, and this equals 6. So eliminating the same variable from the two different sets of 2 equations means that we have to eliminate the x's again. I wouldn't want to eliminate the y's or the z's because we're trying to eliminate x. So trying to eliminate x, again, it would be very forward to say, okay, well, let's take a -1 times the whole first equation and rewrite this. So we get -3x, positive y, minus z equals +1. And then our second equation, which we didn't change at all, is still 3x plus 3y plus 2z equals 6. And by the way, when I say second equation, I mean the second equation of these two. It is technically the third equation that we had from the original system. So now when we do this, our x's eliminate again, and what we get left with is 4y plus z, and this equals 7. Again, let's put a box around this. So we've gone through 3 steps here. We selected the variable we wanted to eliminate. We selected 2 of the 3 equations, wrote them off to the side, and then eliminated the chosen variable. And then we went back and we chose 2 different equations than the ones we chose in step 2 and eliminated the same variable. So what I want to say at this point is you should notice that we're left with these 2 equations that each have 2 variables, but the benefit to having 2 equations and 2 variables is they have the same 2 type of variable. And so we can make with those a new 2x2 system, which is a lot easier to solve than a 3x3 system. So what I'm going to write here for step 4 is this. We should, at this point, have 2 new equations having the same types of variables. So we're going to stack these to make a 2x2 system and solve for the unknowns. So this now just became solving a 2x2 system from a 3x3 system. So what would that look like when I do this? Well, I tend to, once I've gotten my work done here, put a couple of arrows like this, and I say, well, you know what, I'm going to stack these together. So here comes this 4th step here where I'm going to say, you know, we've got 3y. Let me put this in blue. We've got 3y minus 6z equals -15. And then we've got our 4y plus z equals 7. So in this case, this is our new 2x2 system of doom. And the thing is, we want to go solve this. So we got to choose, well, what do I want to solve for? Or what do I want to eliminate here to solve for my unknowns? So in terms of y's and z's, I think it'd be a little bit easier to eliminate my z's here because then I could just take this bottom equation times a +6 and I would have a +6z. So that is exactly what I'm going to do here. I'm going to take everybody down here times 6 and I'm going to say, you know what, I'll rewrite my system off on the side. So my first equation, 3y minus 6z equals -15, and my second equation, which now has become 24y's plus 6z's equals 6 times 7 is 42, we end up with our z's canceling out. So what I get left with here then is 27y's, and this is equal to 42 minus 15. So let's just check this out here, 42 minus 15, and so we get 27. So now you're thinking, you know, this is really ugly, but you know, not always the case, but it tends to be the case that when you solve something like this, you end up with nice integer values, at least if your math teacher is just teaching you this for the first time. So we get y is 1. So first things first, once we know y is 1, I want you to come down here where it says solutions, and what we're going to do is we're going to fill in the y part of our ordered triple with 1. We think y equals 1. And then the neat thing about this is, once I know y, how do I solve for the other variables here? Well, I'm going to put in a 5th step here, and basically we're going to use a word here. We're going to use the value of the, let's put it this way. Use the value that you find in step 4 to back solve for the other unknown value in your 2x2 system. So essentially what I'm saying is, now I know y. So what else can I go find? Well, go back to your original 2 by 2 system here and you say, well, if I know y, then I could plug that back into either of these equations to go solve for z. And keeping in mind that what I want to do is solve for z, and I know that it doesn't matter which of these two equations I plug it back into, I'm inclined to go plug our y back into here for y, because it is a lot easier to get z by itself. So I'm going to rewrite this here. We say 4y plus z equals 7. And instead of y, we're going to put in 1, which we think y equals. So what this becomes now is 4 plus z equals 7. And solving this by subtracting 4 from either side gives us the statement that z equals 3. Now I'm going to put a box around that. I'm also going to run over here and say, now I think I know z. So the thing here is this. After we've done this and solved for the other unknown in our 2 by 2 system, we're going to take our two now knowns, take two known values and substitute into original system and solve for last unknown. So I'll try to squeeze that in there. So essentially, when you look at this, we're saying that now I know y, and now I know z. And because I know y and z, and I know that y and z are the same in any of these equations, because really the system solution has to satisfy everybody, what we need to find now is x. And so what we're going to do is we're going to take these two knowns and plug it back into any of our three original equations, and we're going to solve for x. So since it doesn't matter which one of these three I plug it back into, I'm probably going to go with the first equation just because the coefficients of y and z are both 1 or negative 1, and that's easier to deal with algebraically. So here's what I'm going to do. This first equation that we started with, 3x minus y plus z equals negative 1, I'm going to go back and plug in for y and z these unknown values that we have. And so what we've determined is that y is 1, z is 3. I just want to simplify this now and solve for the remaining unknown. So combining like terms, a negative 1 and a positive 3, that is a positive 2, and that equals negative 1. So subtracting 2 from both sides here, we end up with 3x equals negative 3, which would imply that x equals negative 1. So negative 1, I'll box that and I'll put this down here. We think this is the solution. So the very last thing that I want to do is I just want to make sure my solution works. So what you're going to see me do is grab a calculator, and I'm just going to go substitute these all back in for x's, y's, and z's in each equation to make sure that I get true statements. So for instance, in my first equation, we have 3 times x. Well, that would be 3 times negative 1. And this would be plus or minus y, which would be 1. And this would be plus z, which in this case, we think z is 3. When I hit enter here, I get negative 1, meaning that the left side of this became negative 1, but negative 1 equals negative 1, meaning that this point does satisfy the first equation. So let's check out our second two equations here. 3 times x, we think x is negative 1, so 3 times negative 1. And then we have plus 2 times y, and y is 1, so 2 times 1. And then we have minus 5 times z, which in this case we think z is 3, so 5 times 3. And again, I get negative 16, and negative 16 equals negative 16. In the last equation, 3 times x, so 3 times negative 1. And then we have this, plus 3 times y, so plus 3 times 1. And then we have plus 2 times z, and z is 3 here, so 2 times 3, and we get 6, so 6 equals 6. So going through all of this work is a lot of work, but we can't always check our solutions by plugging it back into these original equations. So to give it to you in a nutshell here, essentially, when we get this system, we're just going to choose to eliminate x, y, or z. But once we've done that, we're going to choose two different pairs of equations to eliminate the same variable in, leaving behind a couple of equations that have the same two variables left over. But that set of two equations there allows us to make that 2 by 2 system and solve down for at least one of our variables. And then at that point, we're just plugging it back into the 2 by 2 system to find the other unknown, and then taking these two unknowns and plugging it back into any of your 3 by 3 equations to find the third unknown. So solving a 3 by 3 system, this is this method that I want you to use here. Cheers.